Tonight, we're going to take a journey that will fundamentally change how you see your place in the cosmos. We're going to explore something that sounds deceptively simple, but is actually one of the most mind-bending realizations in all of astronomy. We're going to discover the true scale of our home galaxy, the Milky Way, and where it really sits in the grand cosmic hierarchy. Because here's the thing most people never grasp. The Milky Way is genuinely massive. It's one of the largest galaxies in the entire observable universe, sitting comfortably in the top tier of galactic giants. But at the same time, when you zoom out far enough, when you start seeing the universe at its larger scales, our home galaxy becomes almost nothing, a speck of dust in structures so vast they defy human comprehension. And I promise you, by the end of this journey, you're going to feel very different about that faint band of light you sometimes see stretching across the night sky on a clear, dark night. Before we dive in, if you enjoy these kinds of cosmic explorations, a quick like or subscribe would genuinely help keep this channel going. It's a small gesture, but it makes a real difference. Now let's begin this journey from home outward, from the familiar to the incomprehensible. Let's start with what we actually know, with hard numbers and observations. You've probably heard people say the Milky Way is big. And yes, it is big. Actually, that's a massive understatement. The Milky Way isn't just big, it's genuinely enormous. One of the largest galaxies in the entire observable universe. Now, I know that might sound surprising, especially when you hear about supermassive elliptical galaxies or galaxy clusters. But here's the crucial truth that almost nobody realizes. The vast majority of galaxies scattered throughout the cosmos are actually tiny compared to the Milky Way. Most galaxies in the universe are dwarf galaxies, small, faint collections of just a few billion stars or even less, barely visible even with powerful telescopes. The Milky Way, in direct comparison, is an absolute giant. The Milky Way stretches approximately 105,000 to 110,000 light-years from one edge to the other, depending on how you measure it and what you count as the edge. That's a distance so staggeringly enormous that light itself, travelling at roughly 186,000 miles per second, takes over 100,000 years to cross from one side to the other. Think about that for just a moment. Light from one edge of our galaxy, light that's moving faster than anything else in the universe can move, won't reach the opposite edge for 100,000 years. A photon leaving one side of the Milky Way today won't arrive at the other side until humanity, if we still exist, is completely unrecognizable. Inside this massive spiral structure, we have somewhere between 100 billion and 400 billion stars. The exact number is genuinely hard to pin down because, well, counting stars in a galaxy you're actually inside of is like trying to count every single tree in a vast forest while you're standing right in the middle of it. You can see some stars clearly, the bright ones nearby, but most are hidden behind others, obscured by vast clouds of dust and gas, blocked by distance and intervening matter. Our Sun is just one of these stars, one anonymous yellow dwarf among hundreds of billions. It sits about 26,000 to 27,000 light-years from the galactic centre, tucked into a minor spiral arm called the Orion Spur, sometimes called the Orion Arm. We're not at the centre of anything important. We're not in some special location. We're in the galactic suburbs, in a relatively quiet, boring neighbourhood, where stars aren't too densely packed together, and catastrophic supernova explosions are rare enough that life had a genuine chance to develop and survive for billions of years without being sterilized by radiation. The Milky Way has been our home for as long as humans have existed, for as long as Earth has existed, for as long as our sun has been shining. Every single star you can see with your naked eye on a clear, dark night is part of our galaxy. Every constellation you've ever learned, every meteor you've ever watched streak across the sky, every planet visible without a telescope, all of it belongs to this one enormous structure. For most of human history, for thousands of years of civilization, we didn't even know there was anything beyond it. We thought the Milky Way was the entire universe. Ancient philosophers looked up at that band of light and called it the river of heaven, the pathway of souls, spilled milk from a goddess. They had no idea they were looking at billions of stars in our own galaxy. They had no concept of what a galaxy even was. But here's where things start to get genuinely interesting, where the paradox begins to emerge. The Milky Way is genuinely, objectively large. In fact, when astronomers survey the universe and catalogue galaxies, they find that about 95% of all galaxies in the observable universe are smaller than the Milky Way. Think about that statistic for a moment. 95%. That means when astronomers point their telescopes at distant regions of space and count galaxies, the vast majority of what they find are small dwarf galaxies, tiny collections of stars that barely qualify as galaxies at all. The Milky Way is actually in the top 5% by size. That genuinely makes us exceptional, not average. We're not living in a typical galaxy, we're living in one of the big ones. Yet here's the paradox, the thing that makes this topic so fascinating. Despite being one of the largest galaxies around, when you start zooming out, when you start looking at progressively larger and larger cosmic structures, the Milky Way begins to shrink in significance. Not in actual physical size, obviously, but in relative importance, in context. It becomes one piece, one component in structures so incomprehensibly vast they dwarf even a large galaxy like ours. And that's the fundamental paradox we're going to explore tonight. This journey through scales, how the Milky Way can be both genuinely enormous and genuinely tiny at the exact same time, depending entirely on what scale you're looking at, what you're comparing it to. But before we zoom out to those incomprehensible scales, let's first understand what makes the Milky Way large. Let's look at its structure, its composition, its place among its immediate neighbours. Because the Milky Way isn't alone out here in the cosmic void. It has neighbours, quite a few of them actually, and understanding these neighbours is the first step in understanding our place in the larger universe. The closest large galaxy to us is Andromeda, also called M31, which sits approximately 2.5 million light-years away from us. Now, 2.5 million light-years is an almost incomprehensible distance. Light from Andromeda that reaches your eyes tonight left that galaxy 2.5 million years ago, when our ancestors were early hominids just beginning to use stone tools, long before anything resembling modern humans existed. You're seeing Andromeda as it was in the deep past. Andromeda is actually bigger than the Milky Way, noticeably bigger. It contains around 1 trillion stars, more than twice what we have in the Milky Way, possibly even more depending on recent estimates. It's a magnificent spiral galaxy, and if you're in a dark location far from city lights, you can actually see it with your naked eye as a faint fuzzy patch in the constellation Andromeda. It's the most distant thing you can see without a telescope. Here's something fascinating. Andromeda is on a direct collision course with the Milky Way. The two galaxies are falling toward each other, drawn together by mutual gravitational attraction. But don't worry, don't start planning for the apocalypse. This collision won't happen for another 4.5 billion years, give or take a few hundred million years. And when it does happen, when these two massive galaxies finally meet, it won't be a violent crash. It'll be more of a slow merger, a cosmic dance that takes hundreds of millions of years to complete. The distances between individual stars are so vast, so impossibly large, that actual physical collisions between stars are incredibly, almost impossibly unlikely. The galaxies will pass through each other like two clouds of smoke, their stars rearranging themselves through gravitational interactions, eventually settling into a new, larger elliptical galaxy that astronomers have already nicknamed Milky Way. Then there are the Magellanic Clouds, two smaller irregular galaxies that orbit the Milky Way like satellite galaxies, like moons orbiting a planet. The Large Magellanic Cloud contains approximately 10 billion stars and sits about 160,000 light-years away. The Small Magellanic Cloud has a few billion stars and is slightly farther. They're both visible from the southern hemisphere as fuzzy, cloud-like patches in the night sky, bright enough to see with your naked eye. Indigenous peoples of the southern hemisphere have known about them for thousands of years, weaving them into their myths and navigation systems. But people didn't realize they were separate galaxies, distinct stellar systems outside our own, until relatively recently in astronomical history, until we had the telescopes and understanding to recognize what we were seeing. These galaxies, the Milky Way, Andromeda, the Magellanic Clouds, along with about 50 to 80 other smaller galaxies, form what astronomers call the local group. It's basically our cosmic neighborhood, our immediate galactic environment. Most of the galaxies in the local group are small dwarf galaxies, tiny things with just a few billion stars or even less, barely qualifying as galaxies at all. Some are so small and faint they're incredibly difficult to detect. The Milky Way and Andromeda are absolutely the two dominant members, the two heavyweight galaxies, the big siblings in a family of much smaller galaxies that either orbit around them or float in the space between them. The local group spans approximately 10 million light-years across from edge to edge. That sounds absolutely massive, and it genuinely is massive by any human standard. But here's where things start to get interesting, where we take the first step in understanding scale. The local group, this collection of dozens of galaxies spanning 10 million light-years, is just one tiny cluster, one small grouping in much, much larger cosmic structures. It's a neighborhood in a city, in a state, in a country. We're zooming out now, and the Milky Way is about to get smaller. The local group is part of something astronomers call the Virgo supercluster. Now, a supercluster is exactly what it sounds like. It's a cluster of galaxy clusters, a collection of collections. Instead of talking about individual galaxies anymore, we're now talking about entire groups of galaxies, hundreds or thousands of galaxies at a time, all gravitationally bound together in enormous cosmic structures. The Virgo supercluster contains at least 100 separate galaxy clusters and groups. One of the largest and most massive is the Virgo cluster itself, which sits approximately 54 million light-years from us toward the constellation Virgo. The Virgo cluster contains somewhere around 1,300 to 2,000 galaxies, depending on how you count them and where you draw the boundaries. Some of these galaxies are enormous, far bigger than the Milky Way. M87, for example, a giant elliptical galaxy at the heart of the Virgo cluster, contains several trillion stars and is home to one of the most massive black holes we've ever observed, the one that was famously photographed by the Event Horizon Telescope in 2019, giving us our first direct image of a black hole's shadow. The Virgo supercluster as a whole contains approximately 100 trillion stars spread across about 110 million light-years of space. Let me put that in perspective for you. Let me make this scale clear. Remember how the Milky Way seemed absolutely massive at 105,000 light-years across? The Virgo supercluster is roughly 1,000 times wider. Our entire galaxy, with all its hundreds of billions of stars, with all its spiral arms and dust lanes and nebulae, is just a tiny speck in this larger structure. If the Virgo supercluster were the size of a large city, the Milky Way would be smaller than a single house in that city. Actually, it would be more like a single room in one house in one neighborhood. We've become small. But even this isn't the full picture, not even close. Because in 2014, astronomers made a discovery that changed our understanding of cosmic structure. they discovered that the Virgo supercluster itself, this massive collection of 100 galaxy clusters spanning 110 million light-years, is just a small part, just one lobe of an even more massive structure called Laniakea. The name Laniakea comes from Hawaiian and means immeasurable heaven, which is beautifully fitting because Laniakea is almost incomprehensibly large, difficult for human minds to truly grasp. Laniakea is essentially a supercluster of superclusters, a structure of structures. It contains approximately 100,000 galaxies spread across roughly 520 million light-years. All of these galaxies, including ours, every single one of them, are slowly moving through space, flowing like water toward the gravitational center of Laniakea, drawn inexorably by the combined gravity of all that concentrated mass. The Milky Way isn't just sitting still in space, fixed in position. We're falling, moving at tremendous speed along with everything else in Laniakea toward a region astronomers call the Great Attractor, a gravitational anomaly, a region of space with abnormally high mass concentration located roughly 150 million light-years away from us. We're moving toward it at about 600 kilometers per second, and there's nothing we can do about it. The entire local group, Andromeda, the Milky Way, all our satellite galaxies, we're all being pulled in that direction by gravity on scales we barely understand. Now here's where the scale truly starts to mess with your perception, where it becomes almost impossible to maintain an intuitive grasp. If you somehow shrunk Laniakea down so that the Milky Way, our home, was reduced to the size of a single grain of sand, Laniakea itself would be roughly as big as a large room, maybe bigger. We've gone from thinking the Milky Way was everything, was the entire universe, to realizing it's less than a speck of dust in a structure so large it challenges human comprehension. And we're still not done. We're not even close to done. This is just the beginning of understanding cosmic scale. Laniakea is genuinely huge, incomprehensibly vast, but it's still just one supercluster among many scattered throughout the observable universe. When we zoom out even further, when we expand our view to truly cosmic scales, we see that the universe is absolutely filled with these enormous structures. Superclusters separated by vast voids, enormous empty regions of space where very few galaxies exist at all. The universe at its larger scales looks like a cosmic web, like foam, like the structure of a sponge. Massive filaments of galaxies stretch across hundreds of millions or billions of light-years, connected by threads and sheets of matter, separated by enormous empty voids where almost nothing exists. This cosmic web structure is one of the most beautiful and mysterious patterns in all of astronomy. Imagine billions of galaxies arranged not randomly, but in this intricate web-like pattern, clustered along filaments, concentrated at nodes where filaments intersect, with vast empty spaces in between. The voids can be hundreds of millions of light-years across, regions where you could travel for unimaginable distances and encounter almost no galaxies at all. These aren't empty because galaxies avoided them. They're empty because of how the universe evolved, how gravity pulled matter together in some regions while leaving others relatively barren. The observable universe, the part of the universe we can actually see with our telescopes, the region of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. Yes, you heard that right. 93 billion light-years, even though the universe is only about 13.8 billion years old. This seems impossible at first, seems to violate the speed of light, but it doesn't. The universe itself has been expanding this entire time, and that expansion stretched space itself, meaning objects that were relatively close to us in the early universe are now much, much farther away due to the expansion of space between us and them. Light from the most distant objects we can see has been travelling for nearly 13.8 billion years. But those objects are now much farther away than that because space has been expanding the entire time the light was travelling. Within this observable universe, within this 93 billion light-year sphere centred on Earth, there are approximately 2 trillion galaxies. 2 trillion. Each one a collection of millions, billions, or even trillions of stars, each one potentially containing countless planets, moons, asteroids, comets, each one a complete stellar system with its own history, its own structure, its own story. And the Milky Way is just one of them, one galaxy among 2 trillion others. Let me make this scale absolutely clear with a thought experiment. Imagine you could somehow shrink the entire observable universe down to the size of Earth. In this scaled-down model, in this miniature universe, the Milky Way would be about the size of a small coin, maybe a dime or a quarter. That's how much space we occupy in the grand scheme of things. We're a coin on a planet-sized structure. Now, in this same scaled model, our entire solar system, everything, orbiting the Sun out to the Kuiper Belt and beyond, would be far smaller than a single atom. You wouldn't be able to see it even with the most powerful microscope ever built. And Earth? Earth would be so small, it would essentially not exist at this scale. It would be smaller than subatomic particles. That's the true scale we're dealing with. That's where the Milky Way sits in the cosmic hierarchy. We're genuinely large compared to most galaxies, genuinely impressive by that standard. But we're microscopically small compared to the universe as a whole. Both statements are absolutely true simultaneously. But here's something that makes this even more mind-bending, even more difficult to grasp. The observable universe, that 93 billion light-year sphere containing 2 trillion galaxies, is almost certainly not the entire universe. It's just the part we can see, the part from which light has had time to reach us. The actual universe beyond what we can observe could be vastly larger. It could be infinite, extending forever in all directions. Or it could be finite but so large that the observable universe is just a tiny fraction of it, like a marble in an ocean. We have no way to know for certain because we can't see beyond the cosmic horizon, can't receive light from regions so far away that light hasn't had time to reach us yet. Some cosmologists estimate the entire universe could be at least 250 times larger than the observable universe, meaning there could be trillions upon trillions of galaxies out there beyond what we can ever hope to see, forever beyond our cosmic horizon. Other models suggest the universe could be truly infinite, meaning there's no edge, no boundary, just space and galaxies extending forever. If that's true, if the universe is genuinely infinite, then the Milky Way is literally infinitely small by comparison. Not just very small, infinitely small, an infinitesimal point in an infinite expanse. Now, you might be wondering why I keep emphasizing that the Milky Way is large when I've just spent all this time explaining how small it is in the cosmic context, and that's exactly the point. That's the paradox at the heart of this exploration. Both perspectives are true, both scales matter. The Milky Way is simultaneously enormous and tiny, and which one you focus on depends entirely on your frame of reference, on what you're comparing it to. Let's zoom back in for a moment, back to human scales, back to something we can actually relate to. From our perspective as humans living on Earth, the Milky Way is so large it might as well be infinite. You could point the fastest spacecraft humanity has ever built in any direction and fly for millions of years, and you'd still be nowhere near leaving the galaxy. Voyager 1, our most distant spacecraft, has been travelling away from Earth for over 45 years at about 38,000 miles per hour. It's now about 15 billion miles from Earth, farther than anything humanity has ever sent, and yet it's barely left the solar system. It would take Voyager 1 approximately 450 million years to cross the Milky Way at its current speed. That's how large our galaxy is from a human perspective. Every star you've ever seen with your naked eye, every constellation in every ancient myth, every planet visible in the night sky, all of it exists within a region of space less than a few thousand light years across, a tiny bubble around Earth within the much larger Milky Way. We can only see the nearest stars, the brightest ones. The vast majority of the galaxy is completely invisible to us, too far away for our eyes to detect, hidden behind dust and distance. The Milky Way contains everything humanity has ever known. Every human who has ever lived, every civilization that has ever risen and fallen, every work of art, every scientific discovery, every war, every moment of love and hate and joy and suffering, all of it happened here, within our galaxy, on one small planet orbiting one average star. The Milky Way is our cosmic home, our origin, our context. And from that perspective, it's genuinely vast, genuinely infinite for all practical purposes. But zoom out again, pull back to the scale of superclusters and cosmic filaments, and the Milky Way becomes almost nothing, a speck barely worth noting in the grand cosmic structure. Both perspectives are real, both matter. And holding both in your mind simultaneously, understanding that the Milky Way is both enormous and insignificant depending on scale, that's what it means to truly understand our place in the universe. Now let's talk about what makes the Milky Way genuinely large, genuinely exceptional compared to most other galaxies. Because remember, we're in the top 5% by size, and that's not an accident. That's not random chance. The Milky Way has properties that make it stand out among the vast majority of galaxies scattered throughout the cosmos. First, their sheer stellar mass. The Milky Way contains somewhere between 100 billion and 400 billion stars depending on how you count and what recent estimates you trust. More recent observations from the Gaia Space Telescope suggest the number might be closer to 200 to 250 billion, but there's still significant uncertainty. Compare that to a typical dwarf galaxy, which might contain only a few billion stars or even fewer. Some ultra-faint dwarf galaxies discovered in recent years contain only thousands of stars, barely qualifying as galaxies at all. They're more like large star clusters than true galaxies. The Milky Way has hundreds of billions of times more stars than these tiny systems. Second, their structure. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, with spiral arms extending outward from the ends of the bar. This spiral structure is actually relatively rare in the universe. Most galaxies are irregular blobs with no clear structure, or they're elliptical galaxies, smooth and featureless. Spiral galaxies like ours make up only about 60% of all large galaxies, and barred spirals are a subset of that. Having this beautiful organised spiral structure puts us in a special category. Third, there's the central supermassive black hole. At the very centre of the Milky Way, in a region called Sagittarius A, there's a supermassive black hole containing approximately 4 million times the mass of our Sun. That sounds enormous, and it is enormous. But compared to the supermassive black holes in other large galaxies, it's actually relatively modest. M87, the galaxy I mentioned earlier, has a central black hole containing about 6.5 billion solar masses, more than 1,000 times larger than ours. Some galaxies have black holes containing tens of billions of solar masses. The fact that our central black hole is relatively small compared to what it could be suggests our galaxy has had a relatively quiet history, without major recent mergers with other large galaxies that would have fed enormous amounts of matter into the central black hole. Fourth, there's dark matter. The Milky Way, like all galaxies, is embedded in a massive halo of dark matter, invisible matter that we can't see directly, but that we know exists because of its gravitational effects. This dark matter halo extends far beyond the visible edge of the galaxy, possibly stretching 500,000 light-years or more from the galactic centre. The dark matter actually contains more mass than all the stars, gas, dust and planets combined. For every kilogram of normal matter in the Milky Way, there are roughly 5 to 6 kilograms of dark matter. This dark matter halo is what really defines the galaxy's gravitational influence, its ability to capture and hold on to satellite galaxies to interact with neighbouring galaxies. Fifth, there's the halo of globular clusters. The Milky Way is surrounded by approximately 150 to 200 globular clusters, ancient spherical collections of hundreds of thousands or millions of stars each, all orbiting the galactic centre in a roughly spherical distribution. These globular clusters are some of the oldest structures in the galaxy, containing stars that formed over 12 billion years ago, not long after the Big Bang. They're like time capsules, showing us what the early universe was like. Having this many globular clusters is a sign of a large, mature galaxy, with a long, complex history. All of these factors combined make the Milky Way genuinely impressive, genuinely large by cosmic standards. We're not living in an average galaxy. We're living in one of the big ones, one of the complex ones, one of the structured ones. And that matters because it affects everything about our cosmic environment, about the conditions that allowed life to develop on Earth. Large galaxies like the Milky Way have advantages that smaller galaxies don't. They have more heavy elements, more metals in astronomical terms, because they've had more generations of stars living and dying, fusing lighter elements into heavier ones in their cores, and then spreading those elements through space in supernova explosions. Without these heavy elements, planets like Earth couldn't form. Rocky planets need silicon, iron, oxygen, carbon, and all the other elements that don't exist in the early universe that can only be created in stars. Small galaxies often don't have enough star formation cycles to build up significant heavy element abundance. They're still mostly hydrogen and helium, the primordial elements from the Big Bang. Large galaxies also have more stable environments for life to develop. In very small galaxies, a single supernova explosion or a close encounter with another galaxy can disrupt the entire system, sterilizing any planets that might have developed life. In a large galaxy like the Milky Way, we have the advantage of being in a relatively quiet region, far from the chaotic galactic center, but not so far out that heavy elements are scarce. This galactic habitable zone concept suggests that complex life might preferentially develop in large spiral galaxies like ours, in regions like our solar system's location. We might be genuinely lucky to be here. So yes, the Milky Way is large, and that largeness matters. It's not just a number. It's a crucial factor in why we exist, why Earth could form with the right composition, why life had billions of years of relative stability to evolve from single cells to complex organisms to intelligence. The Milky Way being in the top 5% of galaxies by size isn't irrelevant trivia. It's part of our cosmic heritage, part of why we're here thinking about these questions. But let's return to the paradox, to the other side of the scale. Because as impressive as the Milky Way is, as genuinely large as it is compared to most galaxies, it's still just one galaxy among trillions. And when you look at the largest structures in the universe, when you examine superclusters and cosmic filaments, even a large galaxy like ours becomes almost insignificant. The largest single structure ever discovered in the observable universe is the Hercules Corona Borealis Great Wall, a massive filament of galaxies stretching approximately 10 billion light-years across. 10 billion light-years. That's roughly 10% of the diameter of the entire observable universe. It contains billions of galaxies, uncountable trillions of stars. The Milky Way, placed next to this structure, would be like a single grain of sand next to a mountain range. Other enormous structures include the Sloan Great Wall, stretching 1.4 billion light-years across, and the Boss Great Wall, spanning 1 billion light-years. These structures are so large that they challenge our understanding of how the universe could have formed them. There simply hasn't been enough time since the Big Bang for gravity to pull together structures this large, at least according to some models. Their existence suggests we're still missing something about how cosmic structure forms and evolves. Between these massive structures lie the cosmic voids, regions of space hundreds of millions of light-years across where almost nothing exists. The Bhuta's void, for example, is a roughly spherical region about 330 million light-years in diameter containing only about 60 galaxies, when a region that size would typically contain around 2,000 galaxies. If you could somehow be in the middle of the Bhuta's void, looking out in any direction, you would see almost nothing. No nearby galaxies, no clusters, just vast emptiness in every direction for hundreds of millions of light-years. It would be the most isolated place in the entire universe. The Milky Way could fit inside the Bhuta's void 3,000 times over. Think about that. Our massive galaxy, one of the largest around, could be placed 3,000 times inside one void, one empty region of space. That's scale. That's the universe putting our home in perspective. And yet, despite all of this, despite the incomprehensible vastness of the universe and our tiny place in it, there's something remarkable about being here, about existing in the Milky Way. Because the universe is largely empty and dead. Most of space is void, vacuum, nothing. Most planets are lifeless rocks or gas balls. Most stars burn in isolation with no observers to see them. But here, on this one planet in this one solar system, in this one large galaxy, matter organized itself into life. And that life eventually became conscious, eventually started looking up at the sky and asking questions about its place in the cosmos. The Milky Way produced us. This galaxy, through billions of years of stellar evolution, through countless star deaths and births, through the slow accumulation of heavy elements, and the formation of rocky planets, and the emergence of chemistry complex enough to support biology, this galaxy made us. We are literally made of matter that was forged in the hearts of dead stars within the Milky Way. Every atom in your body except for hydrogen was created in a star that exploded billions of years ago, scattering its contents through space, where they eventually clumped together to form our solar system and Earth and you. You're made of the Milky Way. You're the Milky Way become conscious, a small part of this enormous galaxy that has organized itself in such a way that it can think and feel and wonder about its own existence. That's remarkable. That's genuinely extraordinary, no matter how small our galaxy is compared to the universe as a whole. Carl Sagan once said, "We're a way for the cosmos to know itself," and he was absolutely right. The Milky Way doesn't know it's large. It doesn't know it's part of Laniakea, or that it's moving toward the Great Attractor, or that it will merge with Andromeda in billions of years. But you know these things. You, a collection of atoms that formed in this galaxy, you understand what this galaxy is and where it sits in the cosmic hierarchy. The Milky Way understands itself through you. So yes, the Milky Way is small compared to the universe, but it's also everything we have, everything we've ever known, everything we could ever explore. It's home, and home matters, regardless of scale. Perspective matters, context matters. When you look up at the night sky and see that faint band of light stretching across the darkness, you're seeing home. You're seeing billions of stars, all part of the same structure that contains our sun, our solar system, our Earth. You're seeing the galaxy that made you, that gave you the elements in your body, that provided the stable environment necessary for life to evolve over billions of years. That band of light is special, not because it's the largest thing in the universe, but because it's ours. It's where we came from. It's where everything we know came from. And understanding its true scale, understanding that it's simultaneously enormous and tiny, exceptional and ordinary. That's not depressing. That's not nihilistic. That's beautiful. That's profound. It means we're part of something much larger than ourselves, part of cosmic structures that stretch across billions of light years, part of a universe so vast it defies comprehension. But it also means we're genuinely special, genuinely rare, living in one of the largest galaxies around, on one of countless planets, in one of the few places where matter became alive and aware. The true scale of the Milky Way isn't just about numbers and measurements and light years. It's about perspective. It's about understanding that size is relative, that importance depends on context, that something can be both magnificent and insignificant depending on what you compare it to. The Milky Way is large by galactic standards, small by universal standards, and the only home we'll ever know by human standards. All three are true simultaneously. So let me answer the question directly now. Is the Milky Way large? Yes. Absolutely yes. It's in the top 5% of all galaxies in the observable universe by size. It contains hundreds of billions of stars, spans over 100,000 light years, has a complex spiral structure, holds enough mass to gravitationally bind satellite galaxies, and has a long, rich history of star formation and evolution. It's genuinely, objectively large by any reasonable galactic standard. But is the Milky Way small? Also yes. Absolutely yes. It's one galaxy among 2 trillion in the observable universe, a speck in structures like Laniakea that span hundreds of millions of light years, a grain of sand compared to cosmic filaments, billions of light years long, a tiny point in a universe that might be infinite. It's genuinely, objectively small by universal standards. Both answers are correct. The Milky Way is large and small, exceptional and ordinary, massive and insignificant. Understanding this paradox, holding both truths in your mind at the same time, that's what it means to truly grasp the scale of our cosmic home. Before we go much further, let me address something important. All of these numbers, all of these measurements, all of this cosmic scale, it can start to feel overwhelming. It can make you feel small and insignificant. And in some ways, that's true. Individually, on the scale of the universe, we are incredibly small. You're a tiny biological organism on a small rocky planet, orbiting an average star in one galaxy, among trillions. From that perspective, you're basically nothing. But here's the thing that often gets lost in discussions of cosmic scale. Smallness doesn't equal meaninglessness. Being tiny doesn't make you insignificant. In fact, I'd argue the opposite is true. The fact that you're here at all, the fact that you exist as a conscious being capable of understanding these scales, of comprehending the vastness of the cosmos, that makes you extraordinary. The universe is mostly empty space and dead matter. Your organized complexity, awareness, consciousness, your matter that thinks about itself, that's rare, that's special. The Milky Way contains hundreds of billions of stars, and as far as we know, only one of them, our Sun, has a planet with intelligent life. Maybe there are others. The universe is so vast that it seems unlikely we're alone. But we haven't found anyone else yet. We haven't detected any signals, any evidence of other civilizations. It's possible, maybe even likely, that life is common in the universe, but intelligent technological life might be extremely rare. You might be part of something genuinely unusual, genuinely special, and even if intelligent life is common, even if there are millions of civilizations scattered throughout the Milky Way and billions throughout the universe, that doesn't diminish your significance. It doesn't make your experience, your consciousness, your life less meaningful. You're still you, still a unique perspective on the universe, still a valuable and irreplaceable viewpoint. The scale of the Milky Way and the universe doesn't diminish you. If anything, it elevates you, because you're capable of understanding it. You can look up at the night sky, see those distant points of light, and comprehend what they are, how far away they are, how they fit into the cosmic structure. You can hold the entire scale of the universe in your mind, from the smallest subatomic particles to the largest cosmic filaments. That's an incredible ability. That's a kind of power that no amount of physical size can match. So when we talk about the scale of the Milky Way, when we discuss how large or small it is, remember that scale and significance are different things. The Milky Way might be small compared to the universe, but it's also the only galaxy we'll ever know intimately, the only one we can study from the inside, the only one that gave birth to us. That makes it significant regardless of its size. Now let me take you even deeper into this paradox of scale, because there's another way to think about the Milky Way's size, another perspective that makes the whole question even more complex. We've been talking about physical size, about light years and star counts and galactic mass. But there's also temporal size, the scale of time, and the Milky Way is absolutely enormous in that dimension as well. The Milky Way is approximately 13.6 billion years old, almost as old as the universe itself, which is about 13.8 billion years old. Think about that timeline for a moment. Our galaxy formed only about 200 million years after the Big Bang, when the universe was still young and violent and full of the first generation of stars. For 13.6 billion years, this galaxy has existed, evolving, changing, forming new stars, losing old ones, colliding with smaller galaxies and absorbing them, slowly growing larger and more complex. During that immense span of time, billions upon billions of stars have been born in the Milky Way. Most have already died, their lives over, their matter recycled back into the interstellar medium to form new stars and planets. The Milky Way you see today is not the same Milky Way that existed 1 billion years ago, or 10 billion years ago. It's been constantly changing, constantly evolving, a dynamic system that never stays still. Our Sun is only about 4.6 billion years old, meaning it's a relative newcomer. It formed from a cloud of gas and dust that was already enriched with heavy elements from earlier generations of stars. The Sun is probably a 3rd generation star, maybe 4th generation, meaning the matter it's made from has been through multiple stellar life cycles. Before our Sun existed, there were other stars here. Stars that lived and died billions of years ago. Stars whose supernova explosions created the elements that eventually became Earth and you. From a temporal perspective, the Milky Way is vast. Its age encompasses timescales that human minds can barely grasp. 13.6 billion years is such an enormous duration that it's difficult to conceptualize. All of recorded human history, all 5,000 or 6,000 years of civilization, is less than 4% of the Milky Way's lifetime, less than a blink of an eye, less than a single heartbeat. The entire existence of our species, of Homo sapiens, about 300,000 years, is only 2% of the galaxy's age. We're newcomers, recent arrivals in a galaxy that has existed for almost the entire history of the universe, and the Milky Way will continue to exist long after we're gone. Long after the Sun dies, long after Earth is destroyed, the Milky Way will still be here, still evolving, still forming new stars. In about 5 billion years, the Sun will expand into a red giant, engulfing Mercury and Venus and possibly Earth. But the Milky Way will barely notice. It'll lose one middle-aged star and gain a planetary nebula. Business as usual. In about 4.5 billion years, the Milky Way will collide with Andromeda, merging into a new galaxy. But even that won't be the end. The merged galaxy will continue on, continue forming stars, continue existing for trillions of years into the future. until the universe itself becomes cold and dark and dead. From a temporal scale, from the perspective of time, the Milky Way is absolutely massive. It existed long before us and will exist long after us. It has a past and a future that dwarf our entire existence. We're living in one tiny moment in the Milky Way's vast history, one brief flash in its 13.6 billion year story. And that's another way to understand scale, another dimension of size that goes beyond just physical distance. So we've established that the Milky Way is large, both spatially and temporally, impressive by most standards. But now let's zoom out again, let's return to that cosmic perspective, because there's more to understand about how our galaxy fits into the larger universe, more layers to this paradox of scale. When astronomers look at the distribution of galaxies throughout the observable universe, they notice something fascinating. Galaxies aren't randomly scattered through space. They're organized into a hierarchy of structures, each level containing the level below it, like Russian nesting dolls. Individual galaxies group into galaxy clusters group into superclusters, superclusters connect along filaments in the cosmic web, and all of this structure, all of this organization, emerged from tiny quantum fluctuations in the very early universe, microscopic variations in density that gravity amplified over billions of years into the cosmic web we see today. This hierarchical structure means that talking about the Milky Way's size without context is almost meaningless. Large compared to what? Small compared to what? It depends entirely on which level of the hierarchy you're examining. Compared to most individual galaxies, we're large. Compared to galaxy clusters, we're tiny. Compared to superclusters, we're invisible. Compared to the observable universe, we're nothing. Each comparison is valid. Each reveals a different truth about our place in the cosmos. Let me give you a more concrete example of this hierarchy. Walking through each level systematically so you can see how the scale compounds, how each level is vastly larger than the one before it. Start with Earth. Our planet is about 12,542 kilometers in diameter. That's our baseline, our home scale, the level at which we live our daily lives. Earth seems enormous to us because we're small biological organisms. Walking around the entire planet would take months. Flying around it takes hours. It's a huge place from a human perspective. Now zoom out to the solar system. The solar system, if we define it as extending to the outer edge of the Kuiper belt, is roughly 100 astronomical units across, where one astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So the solar system is roughly 15 billion kilometers across. That's about 1.17 million times larger than Earth. The solar system is to Earth as Earth is to a small city. We've already jumped to incomprehensible scales and we've barely started. Zoom out to the local stellar neighborhood. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. A typical stellar neighborhood containing a few dozen stars might span about 30 light-years. That's roughly 284 trillion kilometers. The local stellar neighborhood is about 19,000 times larger than the solar system. We've jumped several more orders of magnitude. Zoom out to the Milky Way. As we've discussed, our galaxy is about 105,000 light-years across. That's approximately 3,500 times larger than the local stellar neighborhood. The Milky Way is to the stellar neighborhood as the stellar neighborhood is to the solar system. Each jump multiplies the scale by thousands. Zoom out to the local group. Our cluster of galaxies spans about 10 million light-years. That's roughly 95 times larger than the Milky Way. We're still in our immediate cosmic neighborhood, and already the Milky Way has become a relatively small component of the larger structure. Zoom out to the Virgo supercluster. At 110 million light-years across, this is about 11 times larger than the local group. The Milky Way is now a tiny speck, one of 100 trillion stars in a structure containing thousands of galaxies. Zoom out to Laniakea. At 520 million light-years across, this supercluster of superclusters is about 4.7 times larger than the Virgo supercluster. The Milky Way is now one galaxy among 100,000, a grain of sand on a beach. Zoom out to the observable universe. At 93 billion light-years in diameter, this is roughly 179 times larger than Laniakea. The Milky Way is now one galaxy among 2 trillion, invisible without powerful telescopes even if you could somehow step outside the universe and look back at it. Do you see the pattern? Each level of structure is hundreds or thousands of times larger than the level below it. The scale compounds exponentially, and at each level, the Milky Way becomes proportionally smaller, less significant, more like a single point in an ever-expanding structure. This is why the question of whether the Milky Way is large or small is so complex. It's both, depending on which level you're examining. But here's something crucial that often gets overlooked in these discussions of cosmic scale. Just because the Milky Way is small compared to the universe doesn't mean it's simple or unimportant. In fact, galaxies like the Milky Way are among the most complex structures in the entire universe. They're not just collections of stars, they're intricate, organized systems with their own internal structure, their own dynamics, their own evolution. The Milky Way has a central bulge, a dense region near the core packed with older, redder stars. It has a thin disk where most of the star formation happens, where spiral arms wind through space, where massive clouds of gas and dust collapse to form new stars. It has a thick disk of older stars with more random orbits. It has a stellar halo of ancient stars and globular clusters extending far beyond the visible disk. It has a dark matter halo providing most of the galaxy's mass and gravitational influence. It has a supermassive black hole at its centre, dormant now but capable of tremendous energy output if it accretes enough matter. All of these components interact with each other in complex ways. Stars orbit the galactic centre, but their orbits aren't simple circles. They're influenced by the spiral arms, by interactions with other stars, by the gravitational potential of the dark matter halo. Gas clouds get compressed by spiral density waves, triggering star formation. Massive stars live fast and die young in supernova explosions, enriching the interstellar medium with heavy elements and triggering new rounds of star formation with their shock waves. Stellar winds and radiation from hot young stars sculpt the surrounding gas into beautiful nebulae. Old stars migrate outward over billions of years, changing the structure of the galaxy. The Milky Way is a dynamic, evolving system, not a static object. It's constantly changing, constantly rearranging itself, constantly forming new stars and losing old ones. Understanding all of these processes, understanding how galaxies work, is one of the major goals of modern astrophysics. And we still don't fully understand it all. There are still mysteries, still open questions, still surprises. For example, we're still not entirely sure how spiral structure forms and persists. The spiral arms you see in pictures of the Milky Way and other spiral galaxies aren't fixed structures made of specific stars. They're density waves, regions where stars and gas temporarily bunch up as they orbit the galaxy, creating the appearance of arms. But why do these density waves exist? What maintains them over billions of years? We have theories, good theories supported by computer simulations, but we're still refining our understanding. We're also still figuring out exactly how the Milky Way formed. Did it grow gradually over billions of years by accreting smaller galaxies? Did it form in a single rapid collapse of a massive gas cloud? Probably some combination of both, but the details are still being worked out. Recent observations from the Gaia spacecraft, which has precisely measured the positions and motions of over 1 billion stars in the Milky Way, have revealed evidence of past collisions with smaller galaxies. We can see streams of stars in unusual orbits, remnants of dwarf galaxies that the Milky Way tore apart and absorbed billions of years ago. The Milky Way is built from the remains of smaller galaxies, a cosmic cannibal that grew large by consuming its neighbours. And there's still so much we don't know about the galaxy structure. We can't easily observe the Milky Way from outside, obviously. We're stuck inside it, looking out through layers of dust and gas that block our view in many directions. Most of what we know about the Milky Way's large-scale structure comes from indirect observations and from comparing it to other spiral galaxies we can see face on. We think the Milky Way has 4 main spiral arms, or maybe 2 major arms and several minor ones. We're still not entirely certain. We think the central bar is about 27,000 light-years long, but different measurement techniques give different answers. There's a lot we're still figuring out about our own home galaxy. The point is, the Milky Way is complex. It's not just large, it's also intricate, organised, structured. It has layers within layers, components within components, processes within processes, and that complexity exists at every level of the cosmic hierarchy. Galaxy clusters are complex, superclusters are complex, the cosmic web is complex. Even individual stars are complex with their own internal structure, their own nuclear fusion processes, their own magnetic fields and stellar winds and eventual deaths. Complexity doesn't correlate with size. The Milky Way is more complex than Laniakea, even though Laniakea is vastly larger. A single living cell is more complex than a galaxy, even though a galaxy is incomprehensibly larger. Complexity is about organisation, about the number of different parts and how they interact, about information, content and structure, and by that measure, galaxies like the Milky Way are extraordinarily complex regardless of how they compare in size to larger cosmic structures. This is worth remembering when we think about scale and significance. Size isn't everything. The Milky Way might be small compared to the universe, but it's also one of the most interesting, most complex, most dynamic structures in that universe. It's a place where matter organises itself into stars and planets, and occasionally into life and consciousness. That's remarkable regardless of how many light years it spans. Let me tell you about another fascinating aspect of the Milky Way's scale. Something that really drives home how large it is from a practical human perspective. Even though the Milky Way is tiny compared to the universe, it's so large that we can't see most of it. We're trapped inside it, and our view is limited by dust, distance, and the sheer number of stars in the way. When you look up at the night sky and see the Milky Way as a band of light stretching across the darkness, you're not seeing the whole galaxy. You're not even seeing most of it. You're seeing a thin slice, a cross-section through the galactic disk from our vantage point inside it. It's like standing in the middle of a forest and trying to understand the shape of the forest from that internal perspective. You can see trees in every direction, but you can't see the forest's boundaries, can't see its overall shape, can't get a true sense of its full extent. Most of the Milky Way is completely invisible to us, hidden behind dust clouds that block visible light. The galactic centre, that dense region 26,000 light-years away, where hundreds of millions of stars cluster together around the supermassive black hole, is completely obscured in visible light. We can only observe it in infrared, radio waves, and X-rays, wavelengths that can penetrate the dust. If we could somehow see in infrared instead of visible light, the night sky would look completely different. The galactic centre would be a brilliant region of light, far brighter than anything we can see with our eyes. And even without the dust, we still couldn't see most of the galaxy. The vast majority of stars are too far away and too faint for our eyes to detect. On the darkest, clearest night, far from any city lights, you can see maybe 2,000 to 3,000 stars with your naked eye. maybe 5,000 if you have exceptional vision and perfect conditions. That sounds like a lot, but remember, the Milky Way contains 200 to 400 billion stars. You're seeing roughly 0.1% of them, 1/1,000,000th of 1%. All those stars you see, every point of light in every constellation, all of them combined represent an infinitesimally small fraction of the galaxy's total stellar population. Even with powerful telescopes, even with instruments that can detect the faintest, most distant stars, we still can't catalogue every star in the Milky Way. There are too many, and many are hidden behind dust or other stars. The Gaia spacecraft, which I mentioned earlier, has measured about 1 billion stars so far, and that's the most comprehensive stellar census ever conducted. But even 1 billion is less than 1% of the galaxy's total star count. We've directly observed less than 1% of the Milky Way's stars. The rest exist only as statistical predictions, estimates based on what we've observed and extrapolated to the regions we can't see. This is another way to understand the Milky Way's scale. It's so large that even with the best technology humanity has ever developed, even with telescopes in space looking continuously for years, we still can't fully observe it. We can't even catalogue all its stars. The galaxy is bigger than our ability to comprehend it in detail. We know it in general terms, understand its overall structure and composition, but the specifics, the individual components, most of those remain unknown and will probably remain unknown forever. Think about that for a moment. The Milky Way, our home, the galaxy we've lived in for our entire existence as a species, is so large that we'll never fully map it, never catalogue all its stars, never visit even a tiny fraction of its stellar systems. It's simultaneously home and vast unknown territory, familiar and alien, ours but forever out of reach. From Earth, travelling at the speed of light, you could reach the nearest star in about 4.2 years. You could reach the centre of the galaxy in about 26,000 years. You could cross to the far side of the galaxy in about 100,000 years. But of course, we can't travel at the speed of light. We can't even get close. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour at its closest approach to the Sun. That sounds incredibly fast, and it is fast by human standards, but it's only about 0.064% of light speed. At that velocity, it would take the Parker Solar Probe about 6,700 years to reach the nearest star. It would take about 40 million years to reach the galactic centre. It would take about 165 million years to cross the galaxy. The Milky Way is so large that interstellar travel, even to nearby stars, remains firmly in the realm of science fiction with our current technology. We're trapped on Earth, trapped in our solar system, trapped in our tiny corner of a vast galaxy. And that galaxy, as large as it is, as impossible as it is for us to explore, is still just one small piece of the incomprehensibly larger universe. This is the paradox at its most visceral, most personal. The Milky Way is so large we'll never explore it, never fully understand it, never visit more than an infinitesimal fraction of its stellar systems, and yet it's so small compared to the universe that it's barely worth mentioning in cosmic terms. Both truths exist simultaneously. Both are real. And here's another layer to this cosmic puzzle. Another way the Milky Way's scale becomes both enormous and insignificant depending on your perspective. Let's talk about what astronomers call cosmic address, your complete location in the universe written out in increasing levels of scale. Your cosmic address starts simple. You live on Earth, a rocky planet with a diameter of about 12,142 kilometers. Earth orbits the Sun, a G-type main sequence star. what astronomers call a yellow dwarf, though it's actually white when you look at it from space. The Sun contains about 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets, dust, everything combined is less than 0.2% of the system's total mass. The Sun dominates our local environment completely. The solar system sits in the Orion Spur, also called the Orion Arm, a minor spiral arm of the Milky Way. We're located about 26,000 light-years from the galactic centre, roughly halfway out from the core to the edge. Our position in the galactic disk puts us in what some astronomers call the galactic habitable zone, a region where conditions are favourable for life. Not too close to the violent, radiation-soaked galactic centre, not too far out in the metal-poor outer regions where rocky planets struggle to form. The Milky Way belongs to the local group, a collection of about 54 galaxies spanning roughly 10 million light-years. The local group sits on the outskirts of the Virgo cluster, the nearest large galaxy cluster, which is itself part of the Virgo supercluster. And the Virgo supercluster is one lobe of Laniakea, that massive supercluster of superclusters spanning 520 million light-years. Laniakea sits in the observable universe, that sphere of space approximately 93 billion light-years across, from which light has had time to reach us since the Big Bang. And the observable universe is probably just a small part, maybe an infinitesimal part, of the total universe, which could be vastly larger or even infinite. That's your cosmic address. Earth, Solar System, Orion Spur, Milky Way, Local Group, Virgo Supercluster, Laniakea, Observable Universe, Universe. Each level contains the previous level. Each level is incomprehensibly larger than the one before it. And at every single level except the last one, the Milky Way is just one component among many, one piece of a much larger structure. When you write out your cosmic address like this, when you see all the layers of structure containing our galaxy, it really drives home how the scale works, how perspective changes everything. The Milky Way is the fourth level in a hierarchy that extends at least 5 more levels beyond it, possibly infinitely more if the universe is infinite. It's large compared to the levels below it, small compared to the levels above it. Exactly in the middle of the cosmic hierarchy from our perspective. But here's something that makes this even more interesting. The cosmic hierarchy doesn't just go up from the Milky Way, it also goes down. We started with Earth in that cosmic address, but we could go much smaller. Earth contains continents, countries, cities, buildings, rooms, furniture, objects, molecules, atoms, subatomic particles, quarks, and possibly even smaller structures we haven't discovered yet. The hierarchy extends in both directions from our everyday human scale. We're somewhere in the middle, larger than atoms but smaller than galaxies, able to perceive and understand structures both vastly larger and vastly smaller than ourselves. The Milky Way sits in a similar middle position in the cosmic hierarchy, larger than stellar systems, smaller than superclusters, significant at some scales, insignificant at others, and that's true for every level of structure in the universe. Everything is large compared to something and small compared to something else. Scale is always relative, size is always contextual. Let me give you another comparison that might help illustrate the Milky Way's scale in a different way. Astronomers sometimes use something called the cosmic calendar, where the entire history of the universe is compressed into 1 year. In this calendar, the Big Bang happens at midnight on January 1st, and right now, this moment as you're listening to this, is midnight on December 31st. The entire 13.8 billion year history of the universe is squeezed into 365 days. On this cosmic calendar, the Milky Way forms around January 10th or 11th, very early in the year, Our galaxy is ancient, nearly as old as the universe itself. The solar system doesn't form until September 1st. Life appears on Earth around September 21st. Complex multicellular life doesn't emerge until mid-December. Dinosaurs appear on December 25th and go extinct on December 30th. Modern humans, Homo sapiens, don't appear until 11:52 p.m. on December 31st, 8 minutes before midnight. All of recorded human history, all of civilization, happens in the last 14 seconds of the year. From this temporal perspective, from the cosmic calendar view, the Milky Way is absolutely ancient and long-lasting. It's been around for nearly the entire year while we've existed for only the last few minutes. The galaxy's lifespan dwarfs ours completely. It existed for billions of years before we appeared and will exist for trillions of years after we're gone. From a temporal scale perspective, we're nothing. We're a brief flash, a momentary flicker in the galaxy's long, slow evolution. But from a spatial perspective, from the cosmic hierarchy we discussed, the relationship is different. We're not smaller than the Milky Way in time, we're smaller in space. We occupy a tiny volume within the galaxy's vast extent. Both comparisons are valid. Both reveal something true about our relationship to our cosmic home. Now let's talk about something that might seem contradictory at first, but is actually crucial to understanding the Milky Way's true scale. Despite everything I've said about how large the galaxy is, despite the hundreds of billions of stars and the 100,000 light-year diameter, the Milky Way is actually mostly empty space. Overwhelmingly empty. Almost entirely empty. Stars are incredibly far apart. The average distance between stars in the galactic disk, in our neighbourhood, is about 5 light-years. That's roughly 47 trillion kilometres. The Sun, our nearest star, is a ball of plasma about 1.4 million kilometres in diameter. That sounds huge, and it is huge compared to Earth. But it's tiny compared to the distance to the next star. If you shrank the Sun down to the size of a grain of sand, about 1 millimetre across, the nearest star would be another grain of sand about 30 kilometres away. That's the typical spacing between stars, grains of sand separated by dozens of kilometres. That's how empty the galaxy is. In the denser regions near the galactic centre, stars are closer together, maybe a light year apart or even less. But even there, even in the most crowded parts of the galaxy, stars are still separated by vast empty gulfs. They're not touching, not even close. The galaxy isn't a solid object. It's more like a very, very thin fog of stars, so diffuse that if you were travelling through it, you'd mostly encounter empty space. If you could somehow shrink the Milky Way down so that stars were only a metre apart instead of light years apart, the galaxy would only be about 20 kilometres across. 20 kilometres. You could walk across it in a few hours. That's how sparse the distribution of stars actually is. The galaxy seems large because the stars themselves are separated by such enormous distances, not because there are so many of them packed closely together. And it's not just the stars. Even the matter within stellar systems is mostly empty space. The Sun makes up 99.86% of the solar system's mass. But even the Sun is mostly empty space at the atomic level. Atoms are mostly empty space. You're mostly empty space. Everything is mostly empty space when you look closely enough. This is another paradox of scale. The Milky Way is simultaneously enormous and nearly empty. Vast and sparse, massive and diffuse. It contains hundreds of billions of stars, but those stars are separated by such immense distances that the galaxy is, on average, emptier than the best vacuum we can create in laboratories on Earth. The average density of matter in the galactic disk is about 1 atom per cubic centimetre. That's far less dense than the interstellar medium in science fiction, which often portrays space as filled with colourful nebulae and dust clouds. Most of space, even within the galaxy, is just vacuum with occasional atoms floating through it. So when we ask whether the Milky Way is large, we also have to ask, large with what? It's large in extent, spanning over 100,000 light years. But it's nearly empty within that extent. The actual matter, the stuff that isn't vacuum, would fit into a much smaller volume if you could somehow compress it all together. The galaxy is large mostly because its components are spread so far apart, not because there's a huge amount of stuff packed into a small space. This relates back to our earlier discussion about complexity versus size. The Milky Way's complexity doesn't come from having lots of matter in a small space. It comes from how that matter is organised across vast distances. The spiral structure, the stellar orbits, the interactions between stars and gas clouds, all of that emerges from the gravitational dance of billions of objects separated by light years. The galaxy is complex because it's organised, not because it's dense. Let me share another fascinating aspect of the Milky Way scale that most people never think about. We've talked about spatial size and temporal duration, but there's also velocity, speed, the rate at which things move. And the Milky Way is moving fast, incredibly fast, in multiple ways simultaneously. First, everything in the galaxy is orbiting the galactic centre. Our solar system, sitting 26,000 light-years from the core, is moving at about 220 kilometers per second, roughly 490,000 miles per hour, in its orbit around the galaxy. At that speed, it takes about 225 to 250 million years to complete one full orbit. This is called a galactic year or cosmic year. The last time the solar system was in our current position in its orbit, dinosaurs hadn't appeared yet. Earth was in the Triassic period. The continents were still joined together in the supercontinent Pangaea. Since Earth formed about 4.6 billion years ago, it has completed roughly 20 galactic orbits, 20 trips around the Milky Way, 20 cosmic years. But we're not just orbiting the galactic centre. The entire Milky Way is also moving through space. We're falling toward Andromeda at about 110 kilometers per second. We're moving toward the Great Attractor at about 600 kilometers per second. We're flowing along with Laniakia's overall motion through the universe, and the entire observable universe is expanding, with distant galaxies receding from us at speeds that depend on their distance, eventually exceeding the speed of light for the most distant ones. Though that doesn't violate relativity because it's space itself expanding, not objects moving through space. All of these motions stack on top of each other. Earth is rotating on its axis at about 1,670 kilometers per hour at the equator. Earth is orbiting the Sun at about 107,000 kilometers per hour. The solar system is orbiting the galactic center at about 792,000 kilometers per hour. The Milky Way is moving toward Andromeda and the Great Attractor at various speeds. Nothing in the universe is truly at rest. Everything is moving, and often moving very fast. From a velocity perspective, the Milky Way is large in the sense that objects within it are moving at tremendous speeds over vast distances. The galaxy isn't static. It's a dynamic system where everything is in constant motion, constantly changing position, constantly rearranging itself. Over millions and billions of years, the galaxy's structure evolves. Stars migrate from the inner disk to the outer disk. Spiral arms form and dissipate. The galaxy absorbs smaller galaxies and grows larger. Nothing stays the same. This dynamic nature is another aspect of the galaxy's scale that's easy to miss if you only think about size and distance. The Milky Way isn't just a big object. It's a big, dynamic, evolving system. It has a history and a future. It changes over time, and understanding that temporal evolution, that change over cosmic timescales, is just as important as understanding its spatial extent. Now, let's address something that might be bothering you. I've spent a lot of time talking about how large the Milky Way is, how it's in the top 5% of galaxies by size, how impressive it is by most standards. But I've also talked about how small it becomes when you zoom out, how insignificant it seems compared to superclusters and the observable universe. You might be wondering, which is it? Is the Milky Way large or small? Does it matter or doesn't it? The answer, as you've probably figured out by now, is both. And yes, it matters. But not in the way you might think. The Milky Way's size, its position in the cosmic hierarchy, tells us something profound about the universe and our place in it. It tells us that the universe operates at scales far beyond human comprehension, that there are structures so vast they make even large galaxies seem tiny. But it also tells us that size isn't everything, that being small compared to the universe doesn't make you insignificant or meaningless. Let me explain what I mean by that. In physics and cosmology, there's a concept called the Copernican principle, named after Nicholas Copernicus, the astronomer who figured out that Earth orbits the Sun rather than the other way around. The Copernican principle states that Earth, and by extension humanity, doesn't occupy a special or privileged position in the universe. We're not at the centre, we're not unique, we're typical, average, unremarkable in cosmic terms. And in many ways, the Copernican principle is absolutely correct. Earth isn't the centre of the solar system. The solar system isn't the centre of the Milky Way. The Milky Way isn't the centre of anything. We're not special by location. We're not in some unique cosmic position. We're in a fairly typical spot in a fairly typical galaxy, in a fairly typical part of the universe. But here's the thing that the Copernican principle sometimes obscures. Just because we're not special by location doesn't mean we're not special in other ways. Just because the Milky Way isn't at the centre of the universe doesn't mean it's not remarkable. The galaxy is genuinely large by galactic standards. It's genuinely complex. It's genuinely old. And it produced us, conscious beings capable of understanding the cosmos. That's special regardless of where it happens or how big the galaxy is. The mistake people sometimes make when thinking about cosmic scale is assuming that size equals importance, that being small means being insignificant. But that's not how the universe works. A single atom isn't important because of its size. It's important because of what it can do, what it can be part of, how it can combine with other atoms to create molecules and chemistry and eventually life. A human being isn't important because of physical size. We're important because of consciousness, because of our ability to think and feel and create and understand. The Milky Way isn't important because it's large, though it is large. It's important because of what it contains, what it's capable of producing. It's important because it's our home, because it gave us the elements we're made of, because it provided the stable environment necessary for life to evolve. That importance doesn't depend on the galaxy being the biggest or the most massive or at the centre of the universe. It depends on what the galaxy is and what it does. So when we ask about the true scale of the Milky Way, when we try to understand where it fits in the cosmic hierarchy, we're really asking a deeper question. We're asking about our place in the universe, about whether we matter, about whether our existence has meaning in a cosmos so vast it defies comprehension. And the answer is complex, nuanced, paradoxical. Yes, the Milky Way is small compared to the universe. Yes, we're tiny and insignificant in terms of physical size and location. But we're also remarkable, unusual, special in our complexity and our consciousness. Both things are true. Both matter. Understanding the scale of the Milky Way means understanding this paradox, holding both truths in your mind simultaneously. Let me tell you about one more aspect of the Milky Way scale that really drives home how extraordinary our situation is. We've talked about how the galaxy is large compared to most other galaxies, about how it's small compared to the universe. But there's another comparison we haven't fully explored yet. How does the Milky Way compare to the only other structures in the universe we know of that harbour intelligent life? The answer is simple, almost absurdly simple. We don't know of any other structures that harbour intelligent life. As far as we can tell from all our observations, from all our searches, from all the radio telescopes listening for signals and all the spacecraft looking for biosignatures, we're alone. The Milky Way might be the only galaxy in the observable universe that contains intelligence, that contains consciousness, that contains beings capable of asking these questions. Now, that's probably not true. The universe is so vast, contains so many galaxies and so many stars and so many planets, that it seems almost impossible for life to exist only here, only in the Milky Way, only on Earth. The numbers favour the existence of other life, other intelligence, maybe even countless civilizations scattered throughout the cosmos. But we haven't found them yet. We haven't detected any signals, any evidence, any proof that we're not alone. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common in the universe, if there are millions or billions of civilizations out there, why haven't we seen any evidence of them? Why haven't they visited us? Why haven't they colonized the galaxy? Where are all the aliens? There are many possible explanations for the Fermi paradox. Maybe intelligent life is much rarer than we think. Maybe it's common but tends to destroy itself before it becomes spacefaring. Maybe the distances between stars are too vast for interstellar travel and communication. Maybe civilizations exist, but we're looking for them in the wrong ways or in the wrong places. Maybe they're deliberately hiding from us. Maybe they're so different from us that we wouldn't recognize them as alive even if we found them. We don't know. It's one of the biggest open questions in all of science. But here's what this means for understanding the Milky Way's scale and significance. If we are alone, if Earth is the only planet with intelligent life, then the Milky Way is incomprehensibly special. It's the one galaxy out of 2 trillion that produced consciousness. It's the one place in the entire observable universe where matter became aware of itself. That would make the Milky Way not just large, not just complex, but uniquely, extraordinarily, almost miraculously important. The most important structure in the known universe, regardless of its size, and even if we're not alone, even if life is common and there are billions of civilizations throughout the cosmos, the Milky Way is still special to us. It's still our home. It's still the only galaxy we'll ever know intimately. It's still the place where we evolved, where we developed science and art and culture, where we first looked up at the stars and wondered about our place in the cosmos. From that perspective, from the perspective of meaning and significance rather than just size, the Milky Way is immeasurably large. It's everything. It's the context for all of human experience, for all of life on Earth, for everything we've ever known or will know. That kind of importance can't be measured in light years or solar masses. It's not about physical size. It's about meaning, about home, about belonging to something larger than yourself. So here's the full answer to the question of the Milky Way's scale, the complete picture that encompasses all the paradoxes and perspectives we've explored. The Milky Way is genuinely large by galactic standards, in the top 5% of all galaxies in the observable universe. It contains hundreds of billions of stars, spans over 100,000 light years, has complex spiral structure, and has existed for nearly the entire history of the cosmos. By those measures, it's genuinely impressive, genuinely exceptional. But the Milky Way is also small compared to larger cosmic structures. It's one galaxy among 100,000 in Laniakea, one among 2 trillion in the observable universe. It's a grain of sand on a cosmic beach, a single point in structures that span billions of light years. By those measures, it's tiny, insignificant, barely worth noting. And yet, the Milky Way is also immeasurably large in terms of meaning and significance. It's our home, it's where we came from, it's the galaxy that produced us, that gave us the elements in our bodies, that provided the stable environment for life to evolve and flourish. It might be the only galaxy in the observable universe that contains intelligence and consciousness, or one of very few. By those measures, it's invaluable, irreplaceable, unique. All three perspectives are true. All three matter. The Milky Way is large, small, and immeasurably significant all at once. Understanding this, holding all these truths simultaneously, that's what it means to truly grasp the scale of our cosmic home. When you look up at the night sky tonight, when you see that band of light stretching across the darkness, remember all of this. Remember that you're looking at one of the largest galaxies in the universe, a massive spiral containing hundreds of billions of stars. Remember that you're also looking at a tiny speck in a universe so vast it contains trillions of other galaxies, structures so large they dwarf even the Milky Way. And remember that you're looking at home, at the galaxy that made you, at the one place in all the cosmos that we know for certain contains life and consciousness. The Milky Way is large, the Milky Way is small, the Milky Way is home. All of these are true, and understanding why they're all true simultaneously is one of the most profound insights you can have about the universe and your place in it. Now let me address some of the unknowns, some of the mysteries that still surround our understanding of the Milky Way and its place in the universe. Because despite everything we've learned, despite all our observations and measurements and theories, there's still so much we don't know. We still don't know exactly how many stars the Milky Way contains. The estimates range from 100 billion to 400 billion, a factor of 4 uncertainty. That's enormous. Imagine if we could only estimate the population of Earth to within a factor of 4, if we said there are somewhere between 2 billion and 8 billion people. That level of uncertainty would be unacceptable for Earth, but for the Milky Way, it's the best we can do. We're still counting, still observing, still trying to nail down the exact number. We don't know exactly how massive the Milky Way is. Recent estimates suggest the total mass, including dark matter, is somewhere between 1 trillion and 1.5 trillion solar masses. But different measurement techniques give different results. Some studies suggest the mass could be even higher, maybe 2 trillion solar masses. We're not sure. And since we can't see dark matter directly, since we can only infer its presence from gravitational effects, getting an accurate mass measurement is extremely difficult. We don't know the exact shape of the Milky Way's dark matter halo. We know it's there, we know it's roughly spherical, and extends far beyond the visible galaxy, but we don't know its precise density profile, its exact shape, whether it's smooth or clumpy. Different theoretical models predict different halo structures, and we don't yet have enough observational data to definitively choose between them. We don't know how many planets exist in the Milky Way. Based on observations from the Kepler Space Telescope and other planet-hunting missions, we estimate there are probably at least 100 billion planets in our galaxy, possibly several hundred billion. Many stars have multiple planets, so there could be more planets than stars. But we've only directly detected a few thousand exoplanets so far. The vast majority of the galaxy's planets remain undiscovered, unobserved, unknown. We don't know how many of those planets are Earth-like, with the right size and composition and distance from their stars to potentially support life as we know it. Estimates suggest maybe 10 to 40 billion Earth-like planets in the Milky Way, but that's based on extrapolating from limited data. We're making educated guesses. The real number could be much higher or much lower. We don't know if any of those planets actually have life. We found no evidence of life anywhere beyond Earth, despite searching for decades. We've listened for radio, signals from alien civilizations. We've looked for unusual chemical signatures in exoplanet atmospheres that might indicate biological processes. We've scanned the sky for megastructures or other signs of advanced technology. Nothing. Either life is much rarer than we think, or we're looking in the wrong ways, or intelligent civilizations don't last long enough to become detectable, or they exist but we simply haven't found them yet. We don't know. We don't know what will happen when the Milky Way collides with Andromeda. We can predict the general outcome. The two galaxies will merge into a new, larger elliptical galaxy. But the specific details, how long it will take, what the final structure will look like, whether our solar system will be ejected or absorbed or destroyed, all of that remains uncertain. Computer simulations give us possibilities, but the actual event won't happen for billions of years, so we can't observe it directly. We don't know if the Milky Way will continue forming stars indefinitely, or if star formation will eventually cease. Currently, the galaxy forms about 1 or 2 new stars per year, a relatively modest rate. But the rate has been declining over billions of years as the galaxy's gas supply gets depleted. Eventually, maybe in another 10 or 20 billion years, the Milky Way might run out of gas completely and stop forming new stars. Or maybe not. Maybe gas will continue accreting from intergalactic space, replenishing the supply. We're not certain. We don't know exactly how the Milky Way formed in the first place. We have good general models of galaxy formation, theories that explain how gas clouds in the early universe collapsed under gravity to form the first galaxies. But the specific history of our galaxy, which smaller galaxies it absorbed, when and how the spiral structure formed, all the details of its 13.6 billion year evolution, much of that remains mysterious. All of these unknowns remind us that our understanding of the Milky Way, despite all our technology and observations, is still incomplete. We're still learning, still discovering, still piecing together the full picture. The galaxy is so large, so complex, so full of mysteries, that we'll probably be studying it for centuries or millennia to come, always finding new questions to answer, new phenomena to explain. And that's actually exciting. It means the story of the Milky Way isn't finished. It means there's still wonder and discovery ahead. It means the next generation of astronomers and astrophysicists will find things we never imagined, will answer questions we don't even know to ask yet. The Milky Way holds secrets, and uncovering those secrets is one of humanity's great ongoing adventures. So when we talk about the true scale of the Milky Way, we're not just talking about how many light years it spans or how many stars it contains. We're talking about the scope of what we know and what we don't know. We're talking about the magnitude of the questions still unanswered. And by that measure, the Milky Way is absolutely enormous. It's a frontier of knowledge, a source of endless questions, a structure so rich and complex that we'll never fully exhaust its mysteries. The true scale of the Milky Way includes not just its physical size, but also the scale of our ignorance, the vastness of what remains to be discovered. And that scale is immense, inspiring, humbling. It reminds us that no matter how much we learn, there's always more to know, always deeper levels of understanding to reach, always new perspectives to gain. Let me leave you with some final thoughts about what the Milky Way scale means for us, for humanity, for our future and our understanding of ourselves. We live in an era of unprecedented cosmic awareness. For the first time in human history, we can look up at the night sky and understand what we're seeing. We know those points of light are stars, massive balls of fusion plasma millions or billions of miles away. We know the Milky Way is a galaxy, a gravitationally bound system of hundreds of billions of stars. We know it's one galaxy among trillions, part of larger structures that span unimaginable distances. We can trace the history of the universe from the Big Bang to today, can predict its future evolution, can place ourselves in the cosmic context with accuracy and precision. This knowledge is recent, historically speaking. 100 years ago, we didn't know other galaxies existed. We thought the Milky Way was the entire universe. 500 years ago, we thought Earth was the center of everything, that the sun and stars revolved around us. 1,000 years ago, we had no idea what stars actually were. For most of human history, for thousands of years of civilization, we looked up at the same night sky but understood almost nothing about what we were seeing. Now we know. Now we understand. And that understanding reveals the Milky Way's true scale in all its paradoxical complexity. We know we're living in one of the largest galaxies around, but also in a tiny speck compared to the universe. We know the galaxy is ancient and vast, but also that it's mostly empty space. We know it contains everything we've ever known, but also that it's probably just one of many homes for life in the cosmos, or possibly the only one. This knowledge changes us. It has to. You can't truly understand the scale of the Milky Way, can't truly grasp where we are in the cosmic hierarchy, without being fundamentally changed by that understanding. It shifts your perspective. It makes everyday concerns seem smaller, less urgent. It makes you appreciate how special and rare and precious our existence is. It fills you with wonder and humility simultaneously. Some people find this knowledge disturbing, even frightening. They look at the vastness of the universe and feel lost, insignificant, meaningless. If the Milky Way is so small compared to the universe, if we're just tiny specks on a tiny planet in a tiny corner of space, then what's the point? Why does anything matter? But I think that's the wrong way to look at it. The scale of the universe doesn't diminish us. If anything, it elevates us. Because we're the part of the universe that knows. We're the matter that became conscious, that looked up at the stars and figured out what they are, that measured the cosmos and understood its structure. The Milky Way doesn't know it's large. The universe doesn't know it's vast, but we know, we understand, and that makes us special regardless of our size. Carl Sagan understood this better than almost anyone. In his famous pale blue dot photograph and reflection, he talked about Earth as seen from billions of miles away, a tiny point of light lost in the vastness of space. He talked about how everyone who ever lived, every human achievement and tragedy, every moment of triumph and suffering happened on that tiny dot. And his point wasn't that we're insignificant. His point was that we need to take care of each other and our planet, that we're all we've got, that our smallness in the cosmic scale makes our existence more precious, not less. The same is true for the Milky Way. Yes, it's small compared to the universe, but it's also our home. It's where we came from, where we belong, where everything we know exists. That makes it immeasurably important, regardless of how it compares to larger structures. And here's something else worth considering. The Milky Way won't always be small compared to the universe. I don't mean it will grow to encompass the cosmos. I mean the universe itself will change in ways that alter the comparison. The universe is expanding, and that expansion is accelerating. Distant galaxies are moving away from us faster and faster. Eventually, in trillions of years, those galaxies will recede beyond our cosmic horizon, moving away so fast that light from them can never reach us. The observable universe will shrink. Galaxies outside our local group will disappear from view one by one. Eventually, after enough time passes, after enough cosmic expansion, future observers in the Milky Way will only be able to see the galaxies in our immediate neighbourhood. The rest of the universe will be invisible, forever beyond reach, receding faster than light. At that point, assuming anyone or anything is around to observe it, the Milky Way will seem much larger by comparison. It won't be one galaxy among trillions in the observable universe. It'll be one of the only galaxies that can be observed at all. The cosmic context will be different. The scale will be different. What seems small now will seem large then, not because it changed, but because the universe around it changed. This is a reminder that scale is always relative, always contextual, always dependent on what you're comparing and when you're making the comparison. The Milky Way's size hasn't changed much over billions of years, won't change much over billions more, but its relative size, its place in the cosmic hierarchy, that changes depending on your perspective, your time frame, your frame of reference. The true scale of the Milky Way isn't a single number or a simple answer. It's a relationship, a comparison, a context that shifts depending on what you're looking at and how you're looking at it. Understanding that, appreciating the complexity and paradox of scale, that's what it means to truly grasp where our galaxy fits in the cosmos. So let me come back to where we started and give you a final, complete answer to the question we've been exploring. What is the true scale of the Milky Way? Where does it really fit in the cosmic order of things? The Milky Way is genuinely large by galactic standards. It's in the top 5% of all galaxies in the observable universe by size, containing hundreds of billions of stars spanning over 100,000 light years, with complex structure and billions of years of history. It's exceptional, not average. It's one of the big ones. That's not opinion or interpretation. That's observational fact based on surveys of galaxies throughout the cosmos. The Milky Way is also genuinely small compared to the larger structures in the universe. It's one galaxy among 2 trillion in the observable universe. A tiny component of superclusters that span hundreds of millions of light years. A grain of sand compared to cosmic filaments, billions of light years long. By those standards, it's almost nothing, barely worth mentioning in the grand scheme of things. That's also observational fact. And the Milky Way is immeasurably significant despite its size. It's our home, our origin, the galaxy that produced us and gave us everything we need to exist. It might be the only galaxy in the observable universe that contains intelligence, or one of very few. It's where every human story has unfolded, where all of life on Earth has evolved, where every thought you've ever had has occurred. By those standards, it's infinitely important, irreplaceable, unique. That's subjective truth based on meaning rather than measurement, but it's no less real. All 3 of these perspectives are correct. All 3 reveal something true about the Milky Way and our place in it, and the true scale of our cosmic home includes all of them simultaneously. The galaxy is large, small, and immeasurably important all at once, and understanding that paradox is key to understanding our place in the universe. When you look up tonight, when you see that faint band of light stretching across the darkness, you'll know what you're seeing now. You'll know you're looking at one of the largest galaxies in existence, a massive spiral system containing hundreds of billions of stars, exceptional by any reasonable standard. You'll know you're also looking at a tiny speck in a universe so vast it contains trillions of other galaxies, structures so large they make even our impressive galaxy seem insignificant, and you'll know you're looking at home, at the one galaxy in all the cosmos that we know for certain gave rise to life and consciousness, the one place where the universe became aware of itself. The Milky Way is large, the Milky Way is small, the Milky Way is home. Remember all 3 truths, hold them in your mind together, and appreciate the profound paradox at the heart of cosmic scale, the way perspective changes everything, the way something can be simultaneously enormous and tiny, depending on what you compare it to. That's the true scale of the Milky Way. Not a single measurement, but a relationship. Not a simple answer, but a complex truth. Not a fact, but a perspective that encompasses multiple facts simultaneously. Understanding it requires thinking in layers, holding contradictions in mind, appreciating that the universe operates at scales both larger and smaller than human intuition can easily grasp. Thank you for joining me on this journey through cosmic scale, through the paradox of size and significance, through the question of where the Milky Way truly fits in the universe. I hope you found it enlightening, maybe even transformative. If you did, please consider liking this video and subscribing to the channel. Your support genuinely helps me continue creating these explorations of the cosmos. And remember, the next time someone asks you if the Milky Way is large, you can give them the complete answer. You can explain that it's one of the largest galaxies in the universe, genuinely exceptional by galactic standards. You can explain that it's also tiny compared to superclusters and cosmic filaments, barely a speck in the grand scheme of things. And you can explain that it's immeasurably important regardless of its size because it's our home, our origin, the galaxy that made us and gave us the capacity to ask these questions in the first place. The Milky Way is large, but the universe is larger. The Milky Way is small, but we are smaller. The Milky Way is home, and that makes it special beyond any measurement of size. All of these truths coexist. All of them matter, and understanding them together, that's what it means to truly grasp the scale of our cosmic home. Sleep well under the stars tonight. Look up at that band of light if you can see it. Know that you're looking at one of the largest, most complex, most exceptional structures in the entire universe. Know that you're also looking at something tiny and insignificant compared to the cosmos as a whole. And know that you're looking at home, at the galaxy that gave you life, at the one place in all of space and time that we know for certain contains beings capable of understanding and appreciating these profound truths. The Milky Way is vast. You have your place in it, right here, right now, in this exceptional galaxy we call home. Good night.